Okay, so now I'm going to do an example of an R and V to COE problem. We've had homework problems like this and practice problems like this, so I will show you the most streamlined way to get through one of these problems using a whiz wheel in addition to your math. I'm going to start with example number 2 here. So we're given R and V, and we're told to find our COEs. We want to recall that if R dot V equals 0, then we know we have to be in a circle at apogee or at perigee. And in this case, we can tell that R dot V is 0, because 7,000 times 0 is 0, negative 7,000 times 0 is 0, and 0 times 8 is 0. So R dot V is 0. So to start with, we need the magnitude, or we want to find A, so we need the magnitude of R and V. So the magnitude of R, in this case, would be the square root of 7,000 squared plus the negative 7,000 squared. The negative is inside, magnitude will always be positive. Okay? So this gives us an R value of 9,899.495 kilometers. Our V is a lot easier. There's only one component. The square root of 8 squared is 8. So right away we know that the magnitude of V is 8, and that's in kilometers per second. So to find A, we're going to start with our specific mechanical energy equation, which is V squared over 2 minus mu over R. Mu is on your equation sheet. It is 398600.5 kilometers cubed per second squared. So we have 8 kilometers per second, the whole thing is squared, including the units, over 2 minus 398600.5 kilometers cubed per second squared over R, which is 9899.495 kilometers. These kilometers will take care of the cube, so we're left with kilometers squared per second squared, kilometers squared per second squared. Our answer will be in kilometers squared per second squared, which is accurate for specific mechanical energy. And we end up with energy of negative 8.265 kilometers squared per second squared. We expect a negative energy for a circular or an elliptical orbit. So now we need A. On your equation sheet, you'll see that energy also equals minus mu over 2A. So A equals minus mu over 2 times our specific mechanical energy. Same mu, it's a constant. This energy that we just solved for will lead us to an A value of 24,114.549, and that's in kilometers. It's a 9. Okay. So because R dot V equals 0, we know that we can only be in those 3 cases: circular, apogee, or perigee. We want to know which one we're at, so we compare A to R. Is A greater than, less than, or equal to? In this case, it's greater than. If they're equal, we'd be in a circular orbit. They're not equal. So if you forget which way to tell, just do a quick sketch of an elliptical orbit with Earth. And we know that this is A and this is A. right? If I'm at perigee, that's my R. And let's use another color here. If I am at apogee, that's my R. So that's R of apogee, where this one is R at perigee. We know we're at perigee because we're closest to the Earth. Here we know we're at apogee, we're furthest from the Earth. And so this A from here to here is much bigger than this red vector. So if A is bigger than R, I have to be at perigee. This A is much smaller than my purple vector. So if A is smaller than R, I have to be at apogee. It doesn't matter how you sketch this. It doesn't matter what scale. If it's an elliptical orbit, off-center to one foci or foci is Earth, more than half is definitely going to be bigger than half. Less than half is definitely going to be smaller than half. So that's how you can tell if you're at apogee or perigee. In this case, my A is a lot bigger than my R. So I'm at perigee. So A is bigger than R. I'm at perigee. So the way I find E, my eccentricity, is using this equation. R at perigee is equal to A times 1 minus E. I want to solve for and find my eccentricity. So that leads to eccentricity is equal to R of perigee over A plus 1. And in this case, you will get 0.589. This R of perigee is this R right here. A is this A right here. You just solved for both of them, magnitude and A, to find our eccentricity. And eccentricity is unitless. Okay, that is actually all the math I'm going to do, and the rest I will use the whiz wheel or deduction. So one thing that we can deduce right away is that argument of perigee is from perigee to where I am. Well, if I'm at perigee, then the angle from perigee to where I am is 0 degrees. I know that right away. So using my whiz wheel now, I'm going to use right-hand rule with these two vectors. So I'll move this up so you can see both. Okay, my R vector is in the positive I direction and the negative J direction. Right, so if this is positive J, this is negative J. Positive I, negative I. So I am equal in magnitude in both the positive I and the negative J direction. So my index finger, or my R, is right here, in between them. I'm in both directions equally. I'm right here. My V is purely in the positive K. Now remember, we said I, J, K is always up to the North Pole. So my R is here, my V is to the North Pole, which means my thumb, which is H, is way over here at this 225. Or, without using the number, we'll say it's between my negative J and my negative I, over here, right? So my R is between I and negative J, I and negative J. My V is in the positive K, straight up. So my H is over here. So I want to spin my whiz wheel until my thumbtack points to where my thumb was pointing. I want my thumbtack to point right here, straight here. So to do that, I have to turn it so that my thumbtack is pointing straight right there. In doing so, I have already solved for my, move that out of the way. I've already solved for RAN and my inclination. When this is straight right here, I have an inclination of 90 degrees. And from my I vector until I get to my N vector is 315 degrees. So I can fill in those. I know that my inclination is 90 degrees, and right ascension of the ascending node is 315. So I'll show you that again. My R is between my positive I and my negative J, which is over here. This is positive J, this is negative J. So there's my R vector pointing this way. And then my V vector, V, is in only the positive K direction. So my V is pointing up. H is perpendicular to both of them over here. So I want to point my thumbtack over here. No matter where it is, I'm going to spin it around and make sure that my thumbtack points straight to right there. Doing so gives me an inclination of 90, and my N vector from I to N, 315. If you can see that 315 on the camera, 315. So that's how I have 90 and 315. But now we need argument of perigee, or small omega. Well, we know that our R vector is pointing between I and negative J, and our R vector is pointing at perigee. We found that by comparing A to R. We're at perigee. So if my R vector is here, and I'm at perigee, I want to point perigee to here. So I just turn this until my perigee also points here. So now I'll go back to my R, V, and H. Go back to my 90-degree inclination. My perigee is pointing in the same way my R was pointing, between my I and negative J. So then the angle from my N vector to perigee, right? From N to perigee, 0 degrees. So we know that the argument of perigee is 0 degrees. And though we found by deduction, without even using the Whiz wheel, that true anomaly was 0 because I'm at perigee, but we can see that here as well with the Whiz wheel, just to prove to ourselves that we had it right to begin with. If our R is here, V is up, they're in the orbital plane, H is over here, that's where my thumbtack is pointing, right there. So R is this way, and perigee is this way. The angle from perigee to where I am is 0 degrees. So my true anomaly is 0. So just from using right-hand rule, I've oriented my Whiz wheel how I need it. From knowing that I'm at perigee, I've oriented my orbit how I need it, right here. So my orbit is facing, and then I can tell all of these based on that. I know my inclination is 90. I know my right ascension of the ascending node, where my N vector points, is at 315. I know that from the N vector to perigee is 0 degrees. I know from perigee to where my R vector is 0 degrees. What I also can tell just from looking is that I'm at the ascending node. The N vector points to the ascending node, right? And if I look straight from the top, and I'm at 90 degrees inclination, I am not in a retro or a prograde orbit because I do not have another arrow to compare to Earth's rotation. This would be prograde. Arrows are in the same direction. This would be retro, arrows are in the opposite direction. I am in a purely polar orbit in this case.